we've studied conic sections, and we had that little clicker quiz where I show a graph, not a graph, but I just show an equation. You have to figure out what kind of graph it is. So those are conic sections graphs in 2 dimensions. So now we want to be able to extend that to identify graphs in 3 dimensions. So let's start with this one. We have x squared plus y squared plus z squared is equal to 1. Does anybody know what this is a graph of? Sphere. So our topic today is quadric surfaces. Yeah, 12.6. We talked about cylinders already, and remember I asked you to expand your idea of a cylinder to not just be a circular cylinder, but also to be anything that can start off as some 2-dimensional object, like a parabola on the XY plane, and then that would get extended and swept along an axis. So these are examples of cylinders, and if you had a 3D graphing program like I have, you could take a look at a graph of x squared plus y squared is equal to 1 in 3 dimensions, and you won't see a circle, you'll actually see a cylinder. You can also take a look at a graph of y is equal to x squared in 3 dimensions, and you won't see a parabola, you'll see a cylinder. So if we take a look at some of these in my graphing program, this is called a graphing calculator. It's a neat and very simple little program. It's owned by a guy who's kind of running a company. And Ron, yeah, I could do that. Pacific Tech. So here's the cylinder, x squared plus y squared is equal to 1. Let's see. You can use transparency so we can see the image of that sphere that's still inside. Or we can make the sphere bigger or smaller. Anyways. Yeah, so the idea is just like lines and planes, the cylinder technically goes off to infinity in the z directions.
Do we tend to balance cylinders?
No. In terms of drawing it, we just draw it and chop it off somewhere. If there was a z in this formula right here, then it probably won't look like a cylinder anymore. So the parabola y is equal to x squared. Again, it gets swept up and down the z-axis. And remember, whatever variable's missing, because I could have done z is equal to x squared, then it would be swept along the axis that's not there.
Can you do that as well as the current one? So like that, except
Z is equal to x squared or y squared?
y squared.
So these are examples of cylinders, and remember that they're just two-dimensional objects that have been stretched out, or I call it swept out in a specific direction. So instead of my crappy drawings over here, why don't I just take a picture of this? You guys are supposed to say, hey, your drawings aren't crappy. You guys don't lie for your professors? Oh, thanks. So these are ideas beyond cylinders, and so that means if you cut it, one of the things we're going to be doing with these surfaces is we're going to cut it using planes, coordinate planes, or things that are parallel to coordinate planes, and we'll see some intersections and try to see how it's graphed. Okay, let's see. Sphere. Let's go back to my drawings. Yeah, my cool drawings. And this is our, I don't know if they consider this a quadric section, but I mean, it should probably be considered a quadric section. It's a sphere. And in 2 dimensions, we have the equation of a circle, x squared plus y squared is equal to r squared. And then if we do something to that, it starts to look a little bit like an ellipse, right? So let's see if we could draw an ellipse in 3 dimensions. Let's label this first. So an ellipse in 3 dimensions. So imagine the equation of an ellipse in 2 dimensions, right? So an ellipse in 3 dimensions would be very similar. Let's have you guys think about doing something to this equation to make it look possibly like an ellipse.
Divide one into variables by 4.
Let's divide. Which one should we divide? Z? What do you think is going to happen before I draw this? What do you think is going to happen to this? So a lot of you guys say shrink. I think I would think about this as expanding more than shrinking. But yeah, it'll shrink in 1 or 2 axes, 1 axis. You think it'll shrink in a Z? You think it'll flatten? You think it'll span in a Z? Think about it. Actually, yeah. So before we draw it, let's think about this. Let's what are we going to do?
If you look at like 2
equal to,
equals, like not being the other one, then you get this to be a circle on x squared plus y squared. When z equals 0 will be a circle.
okay. Let's do some scratch work first. So let's consider x squared plus y squared plus z squared over 4 is equal to 1. Let's do some things. Let's first take a look at letting z equal to 0. Now, z is equal to 0. Tell me about z is equal to 0. What is it? Well, that's the result. But what is z is equal to 0? It's the xy plane, right? So z is equal to 0 is the xy plane. So what you're saying is that when you're letting z is equal to 0, and this is what your response was, Martha, was that you're going to get you took away one of the variables by letting z is equal to 0, and you have x squared plus y squared is equal to 1. So what you have left is a circle. So what that is that if you cut this surface with this plane, xy plane, you're going to get a circle. Does that make sense? All right. Now instead of z, let's let y equal to 0. What is y is equal to 0 as an object? The other two variables, right? X, z. Yeah, so if we put y is equal to 0, we have x squared plus 0 plus z squared over 4. I mean, you can call 4 2 squared. And if you remember the ellipsis, that would be on the x, z, that would have a z intersection of 2. I mean, if you let x equal to 0, for example, you're going to get z is equal to plus or minus 2, right? So, meanwhile, the x is still at 1, so this is an elongated ellipse, elongated along the z-axis. So you can imagine the other parts of that happening. Let x equal to 0, so that's the yz plane. You're going to get y squared plus z squared over 4 is equal to 1. Again, you'll get this elongated ellipse on the yz plane. Now imagine trying to draw this without a computer. And imagine drawing the wires for this surface. And by wires, I mean what's happening in the x-axis, the y-axis, the z-axis. So let's see how tight this drawing is going to be. You could think about it that way. Let's start with this on the xy plane. This is a circle on the xy plane. So let's draw a circle on the xy plane. A radius 1. Now, on the xz axis, that would be my purple graph. My z goes up to 2 now, 1, 2, and negative 2. And that would intersect So we knew that this is going to be like an elongated object, but now we know exactly that it's elongated along the z. It's like taking the z-axis or taking the z. If you take a sphere and you take the z values and you push it out. Look at that drawing. That's badass. It's not. It sucks. What are you guys talking about? All right, so here it is. What? Looks like a pill. Take the red pill and the blue pill. So this is called an ellipsoid. In general, your ellipsoid will have the form x squared over a squared plus y squared over b squared plus c squared over z squared. Is that z on top, c in the bottom? Is equal to 1. And, you know, just like the ellipse, if we move the center, it'll be like x minus x naught, and then you'll have a new center. If the thing that's being squared here is something else. A lot of people haven't gotten their quizzes yet. Just pass it up and give it to Michael, and then come all the way up, and I'll take it. Okay, we good with ellipsoids? So far we got spheres and ellipsoids. Second most recent what? Yes, today. I don't know. All right. So there's this other thing. What are the conic section shapes again? Parabola, ellipse, hyperbola, right? Circles and stuff. So let's backtrack to the parabola. The parabola is x squared plus y squared. Or what? What's a parabola? Y is equal to x squared. Oh man, gotta stop taking those drugs. NyQuil, DayQuil, drugs. Let's take a look at this graph. Z is equal to x squared plus y squared. Now, if we do those cut things again by letting z or x or y equal to 0, we're kind of seeing what happens when we cut it with a plane. Z is equal to 0 doesn't make much sense, but let's write it down anyways. If z is equal to 0 on the xy plane, we're going to get 0 is equal to x squared plus y squared. What? What is this? Only the origin. So this will only happen for exactly one point. That means x is equal to 0 and y is equal to 0. Let's just put the origin. So whatever the shape is, if you try to cut it with the xy plane, all you're going to get is that origin, that one dot. Okay? Let's try cutting it with x. We do x first, y first. Y is 0, doesn't matter. Z is equal to x squared plus 0. So that's a parabola opening up along the z. If you label your axis correctly, x and z. And then we have x is equal to 0. That's the yz plane. You get z is equal to y squared, which is another parabola opening up along the z again. But make sure you label axis. The horizontal axis is the y. Yeah, I think we can do a little bit more. This z is equal to 0 didn't really give us much. Let's try another plane that's parallel to the xy plane, like z is equal to 1. So z is equal to 1, we get 1 is equal to x squared plus y squared, right? So imagine whatever this graph is, it looks like if you cut it straight down, it looks like a parabola straight down in two different axes. It looks like a parabola. And if you cut it at the xy plane, you get a dot. If you cut it a little bit higher, you get a circle. Let's cut it a little bit higher still. Z is equal to 2 maybe. Looks like another circle, right? They're concentric circles, and the circles seem to be getting a little bit larger at each step higher. And so let's do my cool wire drawing frame. It's a dot at the origin. It's a parabola on the xz plane. Another parabola on the yz plane. And then now if you make your cuts a little bit higher, they're going to be circles. Ah, I just blew it. I was doing so good too. Is it a funnel? Because this is kind of smooth in the bottom, right? So it looks like a bowl. Square root of 2. Because it's actually just equal to 2, but I want it to look like r squared. So let's graph it. Yeah. Now this is a weird drawing. All right, let's talk about why they have these corners up here. That's how the program works.
It looks like a square piece of cloth pulled over.
Yeah, so if you look at it directly from the top, it's taking a square as its base. I think that's a good description, what Joe said. If you take the corners of that square and then you move it up, it looks like a square piece of cloth that had been kind of stretched out up along the corners. What? Yeah. So that's the idea behind and Frederick said that this is how the program works. That's the idea behind being able to graph this. Because the way the graphing program works is that it takes x and y values and plugs it in, and then it gives you z values, and then your domain is set as x and y values. So later on we'll see other ways of trying to graph this where the domain doesn't necessarily have to be like some square region on the xy plane anymore. imagine this thing being cut with a plane. Well, let's take a look at the planes that we use to cut. Z is equal to 1, right? It's a circular cut. Maybe I should make this yellow, something different. If you look at it, it looks like that circle. And any other cuts that you make here would also be circles. Well, technically they're supposed to be circles. Right? In fact, it's interesting to look at it, how it would look like from the top. And another cool thing about this program is that we can take a look at it from the top. And what I'm going to do is I'm going to create another image on the side so that you can see the cross-section cuts. So as you move up and down, you'll see the kind of graphs that you'll get. Right? And they're just circles. So, what did you call this, Frederick? No, you... Paraboloid. Yeah, not a hyperboloid. So this is called a paraboloid. More specifically, though, if you look at the cross-sectional cuts that we're making over here, they're circles. So this is can even be further defined as a circular paraboloid. Hmm? It's not quite swept, right? It's no, because that would be a cylinder, right? What? It's download. You pay for it. Well, I don't want to make this an advertisement or anything. So this is called a circular paraboloid. Now, because the cross-sectional cuts are circles, what other shapes can we have if we take a different kind of cross-sectional cut? I meant like if we continue cutting it with a z is equal to something, what other shape might I have over here? Like an ellipse? If you do it at an angle, but I want the regular cuts. So I guess what I'm asking is that, can I change my function, z is equal to x squared plus y squared, so that its cuts are not circles anymore, but maybe ellipse? So if we take one of the x or y and divide it by a nice number, like 4 or 9, right, it doesn't have to be a nice number, divide it by anything, then there's a possibility that our graph would now, what? Maybe that was too big. Let's call it 4. All right, maybe we could zoom out. So that means I have to do that with this one. Divided by 4. So now, instead of circles, we have ellipse. Elliptical. Yeah.
What does it look like if y equals n?
If y equals n?
Yeah, would it still look like an
That would still look like paraboloids. Are you talking about if we cut it with with y is equal to 0 and x is equal to 0?
like y equals n instead of cutting it like obliquely?
Yeah. So if you cut it with a y, it's harder to see, but if you look at it from the side here, we're going to get paraboloid or parabola cuts. Okay, so this graph isn't going to match anymore. Well, it's moving back and forth. Yeah. Again, this maybe you should hide this. So this is what's happening, but if you look at it from the side, it's like cutting parabolas. All right, let's go back to the z cuts and show that the cuts are actually ellipses. Yeah, if you cut it at an angle, then it would look a little bit different. We would get ellipses, but then yeah, I won't get the expanding thing. All right. So by dividing it by some values, just like we do with an ellipse, then we get ellipses, the cross-sectional cuts, and that would make it an elliptical paraboloid. I'm really slow today. Okay. So elliptical paraboloid, and the general term for elliptical or general equation for an elliptical paraboloid is this, and if A and B are both equal to each other, then this thing will end up being a circular paraboloid after all. Yeah?
Are the elliptical paraboloids, hyperboloids, and ellipsoids synonymous with each other? Similar attributes?
Yeah, well, similar. So the actual noun, let's do some grammar here. The actual noun is a paraboloid. That's a paraboloid. So you get a paraboloid if two, you got x, y, z variables. If two of your variables are squared and then the other one is not squared, then you have an elliptical paraboloid or some sort of paraboloid. Maybe not elliptical, maybe circular, maybe this other type of paraboloid that we're going to take a look at. But the idea is that if x and y are squared and z is not, then it's some sort of paraboloid. That's your noun. Elliptical is an adjective that describes the cuts that you make on this surface. So your cuts result in ellipses, so this is called an elliptical paraboloid. Let's go back to the cylinders. These are all cylinders. One of them is a circular cylinder. And then the other ones are parabolic. they're cylinders, that's their noun, but then you're describing them because that's the shape that you get when you cut it. Parabolic cylinder. Okay? So there's one more possible shape with a paraboloid when you do a cross-sectional cut. Yeah, so instead of, you know how you get an ellipse with z is equal to this thing? What if you put a minus sign in between them? And then, then you would get if you let z equal a bunch of different numbers, you're going to get hyperbolas. But it's still called a paraboloid, and so that special name is called the hyperbolic paraboloid. So this is a super cool shape. And I'm going to put a minus sign here. I'm going to take away the 4. And then I'm going to let my n go negative. Before, if n went to negative, because it's x squared plus y squared, it's always going to be positive. So putting a z is equal to negative, like that paraboloid, the z is equal to negative won't intersect anything. But this one would. So let's see. It's a what? A saddle. A camel? What's the difference between a camel saddle and a regular saddle? Oh. So if you move it up and down, I think it's better to look at the cross-sectional cuts and study them a little bit more carefully. And maybe we'll do a little bit of that. But if you move it up and down, you'll see that the pictures on the right side are all hyperbolas. There's one zero, zero. I can't get to 0. Oh, yes. So at 0, 0, if you let z is equal to 0, and when you look at the equation, and this is the equation I want you to look at. Let's get rid of this one so it doesn't get too confusing. If you look at the equation, if you let z is equal to 0, you have x squared is equal to y squared. And then if you take the square root, you'll see that x is equal to plus and minus y, or y is equal to plus and minus x. So that's a y is equal to x line and y equals negative x line. So it actually is 2 lines that come out. What happened? Did I press something? Oh, it's still there. So it turns out that we could see a bunch of different shapes out of this. And by letting these values equal to -1, 0, +1, +2, we'll see that it looks like a combination of a bunch of different hyperbolas. That's just cool, huh? Sit here and stare at it for hours. Take NyQuil and then you might start to visualize the 4th dimension. Wow. What? All right. So this is called a hyperbolic paraboloid. And it's because the cross-sectional cuts are hyperbolas. And remember, the main feature is that two of the variables are squared and then the other one is not. That's the feature of the paraboloid. Paraboloid. Oh man, I just messed it all up. So the main feature of the paraboloid is that one variable two variables are squared and one is not. And the fact that this is the cross-sectional cuts are hyperbolas means this is a hyperbolic paraboloid. And a common term for this is the saddle, for those people that mention saddles. Yeah.
You have y minus x instead. You just change the switch direction.
Yeah. Yeah, so if you switch the x and the y, then it'll switch orientations. It'll still look like a hyperbola, some sort of hyperbola. So it'd still be called a hyperbolic paraboloid, but the shape will be a little bit different. So let's divide this, for example, by 2. It's still a hyperbolic paraboloid. You're still going to get paraboloids. It still looks like a saddle, but it kind of got elongated somewhere. Yeah. Our plane, if we change our plane, then that's a good question. What if you change your plane? What kind of cross-sectional cuts are you going to make? So let's let this run x. What do you think it's going to look like? It's going to look like parabolas, but there's something interesting about the parabolas. Let's look at it. So it look like parabolas, right? And these look like they're upside down parabolas. Now let's go along the y. And this time you got right side up parabolas. So that's the other interesting thing about this, is that if you make your cuts along one axis, you're going to get a parabola with a certain orientation. If you make your cuts on the other axis, it'll be a parabola with the opposite orientation. You have to look at it from here. So these are right side up parabolas, and if we make our cuts on the other side, it'll be okay. Now there's the last one. The last, I guess we'll call them families, is running out of time. If everything was squared, and we're adding everything, we know that it's a sphere or an ellipse, right? So what if we make one of these negative? So this would be called a hyperboloid. Okay, wait before you get too impressed. Ah, come on. Well, minus x. Oh, come on. Just have to write everything. So what I wanted to do is, I'll start over. Minus x squared minus y squared plus z squared. So There's two types of hyperboloids. One type of hyperboloid is when one has a negative and the other two are positive. And then the other type of hyperboloid is when two are negative and one is positive. And these are called hyperboloids, but they are called hyperboloids of one sheet or two sheets.
The top one is one sheet?
Yeah, the top one in blue is the hyperboloid with one sheet, and then the bottom one is the hyperboloid of two sheets. Notice that there's one sheet and two sheets for the hyperboloids. That's why they're called that. Hyperboloid of one sheet and hyperboloid of two sheets. I call it sheets because they're like surfaces. They're made of one surface, two surfaces. Yeah. So there's actually one more. Let's take, let me have you guess. Let's take this one and set it equal to 0. You'll never guess what this is. No? What? It's a cone. What? A cone. All right? So that's our last object. You guys can think about that over the weekend and take some NyQuil. What? Which one? The cone? The cone is just called the cone. One. I don't know. Give me a minute. It's the same. Oh yeah, it's the same because you just bring up something on one side because it's 0. I didn't think about that. Thank you.
On Canvas, you gave me a 0 for the first quiz, but I got a 6 on it.
Is it quiz number 0 or quiz number 1?
Quiz number 1.
Really?
Yeah, because it's -2 and -2.
Yeah.
I
Well,
think it's just because that kind of looks like a 0.
no, okay, I wouldn't give anybody a 0 for actually taking the quiz. You only would have gotten a 0 if you didn't take the quiz. So I don't know what happened to to me when I was entering it, but I'll fix that.
Okay, thank you.
Oh yeah. Fernando. Oscar? Did Oscar leave? Pardon me? No. They're taking the quizzes at the... Yeah, it's coming sometime in a few weeks, so when it gets closer, we'll work things out. Oh yeah, nobody else gave that to me. Yeah.
All right, thanks.
Thanks, Caleb. Bye, Martha. Sure. All right, Oscar, it's here.
I don't know.
All right,
I don't
so
know.
that's
I'm
it.
proposing that Lapuz makes different versions of the quiz.
What?
Do you make different versions of the quiz?
What do you mean?
Like, are there
I might be
versions of
confusing it
alternate
with
questions?
the other quiz I took yesterday. That's why. But it was like, it was like on top version or something.
I don't know.
No.
I don't know.
Maybe I was.
I'm thinking other people might have gotten this wrong because I triple checked the estimation calculation time.
There's no way I'm going to get this wrong. But I probably got it wrong anyways because I'm actually stupid. So,
I don't know. I mean,
because I got the same like cross product factor.
the cross product one. I think I did that one.
Because I got like 14, 0, -7. Yeah. So if you know I got the same cross product. Yeah, she got that one. And I got like, I know I did the magnitudes right because it's just the square root of all the numbers squared added together. And I got like 117 degrees. That's assuming that the -7 was right. Yeah, that was -7. I got root 11. Yeah, because it was one negative 2 negative 1. I'll probably like miss only 1 or 2 points because I just blew up the space shuttle by accident.